Good day. Today we're going to be talking about vapor pressure lowering. So we're going to look at what happens to the vapor pressure as we add a solute into a solvent. So just as a reminder what vapor pressure is. Vapor pressure is going to be the pressure of a vapor in contact with its liquid form. And we can talk specifically about its equilibrium vapor pressure. So when a pure liquid is in a closed container, so one where we cannot have our vapor escape, basically. The equilibrium vapor pressure, which we can only get an equilibrium vapor pressure if we have a closed container, because otherwise our vapor will just go away. So the equilibrium vapor pressure is when vaporization occurs at the same rate as condensation. However, if we are not in a closed container, that doesn't mean we can't talk about the vapor pressure of a substance. We just won't be able to get to an equilibrium vapor pressure because we do not have the liquid staying. But we can basically change the point, the point of equilibrium for that vapor pressure by adding in a solute. So we're basically disturbing our equilibrium. So what happens when we have something that goes from the liquid phase to the vapor phase? It has to be on the surface of the liquid. So if that solute is not on the surface of the liquid, if that solvent is not on the surface of the liquid, it can't escape into the gaseous or vapor phase. So because we have solute molecules in there, we're actually blocking the surface a little bit, which allows for fewer molecules of solvent to escape into the vapor phase. So we have less solvent molecules on the liquid surface. And again, this is because we have solute molecules in the way. So our surface is partially blocked. By solute particles. Okay. Because of that, this leads to fewer molecules escaping into the vapor phase. Okay. Which in turn leads to a lower evaporation rate. additional factors that must be taken into account is now we have a additional substance in there, so there's going to be more collisions between our solute and solvent, which allows for attractions to form, and that attraction keeps our molecules in the liquid phase. Okay, so let's look at what that kind of looks like. So here in A, we have a closed container where we've got our solvent molecules, pure solvent molecules, and we have our equilibrium vapor pressure where condensation and vaporization are occurring at the same rate. We add in a solute. That solute ends up with some of the particles on the surface. As a result, we don't have as great of a rate of evaporation, but the rate of condensation is still occurring. And as a result, as we go back to another equilibrium, we have a lower vapor pressure because there are fewer molecules going into the vapor phase. Okay. Now, we have an equation that we use in order to calculate vapor pressure, and it's called Raoult's law. And we'll do Raoult's law calculations in a further video, but today we're just going to look at the equation. So it's used to calculate the vapor pressure of a solution. And it's a simple equation. Our P of solution is equal to the P naught of the solvent times by chi solvent. Okay, so our P of solution is our vapor pressure of our solution. Our P naught of our solvent is our regular equilibrium vapor pressure for our solvent, or vapor pressure for pure solvent. And then chi is the mole fraction of the solvent in the solution. Okay, so just another note, in the case of Raoult's law, we need a non-volatile solute. So that solute cannot add vapor pressure into this. Okay, we will modify Raoult's law if we have a solute that is volatile. We'll look at that in just a minute. Okay, and in order to obey Raoult's law, we have to have an ideal solution. Okay, so something where we have a volatile solute would not be an ideal solution. But also, if we have an ideal solution, we're assuming our intermolecular forces between our solute and solvent are similar to the intermolecular forces of our solute molecules. So they're very, very similar in energy. They all are dipole-dipole, or they're all hydrogen bonding, or something like that. Okay. So if that is not what's occurring, so if our solvent intermolecular forces are stronger, then our actual vapor pressure will actually be greater than the vapor pressure calculated using Raoult's law. So if our intermolecular forces in the solvent are greater than the intermolecular forces in the solution, the actual vapor pressure is going to be greater than the calculated vapor pressure. So the vapor pressure calculated using Raoult's law. Okay, so that would be considered a area where we have a positive deviation. So we have a greater vapor pressure. Now this is for what you're seeing down here is including two volatile liquids together, but same idea. If we have a positive deviation, the vapor pressure will be greater than what Raoult's law is going to predict for us. Similarly, if we have intermolecular forces that are greater in the solution than in the solvent, then we're actually going to have a negative deviation. Where we have the actual vapor pressure being less than the calculated vapor pressure. So if the solution intermolecular forces are stronger, the actual vapor pressure will be less than the calculated vapor pressure, and we call that a negative deviation. And that's what we see down here, where we have a vapor pressure that is less than what Raoult's law is going to calculate for us. Now, like I said, that we see, these three pictures show that idea of the positive and negative deviation, but these are for mixtures where we have our solute and solvent being volatile. So we do lose ideality due to that. So we lose ideal liquid behavior when the solute is also volatile. And when we have a volatile solute, we have to basically add our solute's vapor pressure to our solvent's vapor pressure to get the total vapor pressure of the solution. Okay. So we're basically going to solve for our vapor pressure of our solvent, solve for our vapor pressure of our solute, add them together, and that will give us our vapor pressure of our solution. So we'll do our vapor pressure calculation. We do our P solvent, so this is when we're actually solving for the vapor pressure of our solvent in a solution, will be equal to our mole fraction of our solvent times by our solvent in its pure form. Okay. And then we're going to add that to our solute. So we'll solve for our vapor pressure of our solute by taking the mole fraction of our solute times by our regular old pure solute vapor pressure. And then we're going to add those together. So our total solution vapor pressure will be equal to the vapor pressure of our solvent plus the vapor pressure of our solute. And this is what that looks like. We will still see a positive and a negative deviation in this case, like we saw up here, if we have intermolecular forces that are different in the solution than they are for the pure solvent. So in general, it's just going to be an additive thing. We add the vapor pressures together to get our vapor pressure of our solution. And generally, the mixture will be somewhere between the two vapor pressures. Okay. And that's everything. So just as a note real quick, vapor pressure, understanding how vapor pressure works and how vapor pressure lowering works will help us to understand boiling point elevation. So hopefully you understood this. Let me know if you didn't. You guys have a great day. Talk to you later.